Today we want to take a look at this problem, which is a non-calculus problem that's going to morph into a calculus problem, classic style of calculus problem. Start by approximating using a line, and then see how far off you are when you actually use the derivative. I had to rewrite part C here because they're saying give the exact value and then round it to 4 decimal places. If you're rounding to 4 decimal places, you're not given the exact value. I don't know what they're talking about. It's kind of a weird way to ask a question. What they want to do is say, do that dot product thing that we talked about in this section, and then see how different it is from your previous answer. All right, so let's set off on finding the things we need to find. First of all, we want 2 points, just like when back in the day when we were finding the slope of the tangent line back in the halcyon days of calculus 1, where we didn't know any stuff and we were just learning. We wanted to find the slope of a tangent line, and we did that by finding the slope of a secant line. We picked something that was nearby, and we are doing the same thing here. Pick a point that is near the point 6, 3. But it's in this direction of -I plus 4j. So I'm going to take the point 6, 3, and I want to go in the direction of -I plus 4j. So I'm going to take the point P. So P is 6, 3. And I want to go a distance of 0.1 in the direction of V. But V has a length of square root of 17, it looks like. So I can't just do 0.1 times V. Because that will give me too much length of V. What I want is a unit vector in the direction of V. So I'll take the V and we'll divide it by the length of V. And this will be the location of the point Q. Any questions about my procedure? I want to start at the point P. I want to go 0.1 in the direction of V, but I've got to get just the direction out of V. I got to extract just direction information out of that. So I'm going to make a unit vector in the direction of V. So V is, well, let's make sure I got the right magnitude of V. The square root of -1 squared plus 4 squared square root of 17. So I'll have 6, 3 plus 0.1 times -1 over root 17 and 4 over root 17. So I just need to make these 2 calculations to find Q. 6 minus 0.1 over the square root of 17. And then 3 plus 0.4 over the square root of 17. So it looks like Q, rounded to 5 decimal places, is going to be 5.97575. And the Y coordinate will be 3.09701. Oops, I spelled decimal point really wrong. Three point 09701. So there's our point Q. I know I listed it as a vector and not a point, so Q is at the end of that vector. So now what we want to do is approximate the directional derivative of f of xy, square root of x plus y, in the direction of v. So we're just going to use p as the starting point and q as the end point, and we'll divide by how far we went. So the directional derivative I'm just going to put it, I don't have a name for it. So it's going to be how much f changes divided by how far we went. So we're just going to look at the value of f at q minus the value of f at p divided by 0.1. Where we ended up minus where we started divided by 0.1. So f of q I believe this whole problem was constructed just to make teachers say f of q. Because we've cleverly avoided saying this derivative as fu by replacing the unit vector u with the unit vector v. But that's all beside the point. So I need to evaluate the function at the point q and at the point p. So I'll have the square root of 5.97574637 minus, or sorry, plus. Fortunately, I have that one right there. So here's going to be f of q, 3.01210. And then we will need f at p, which is also a square root. So we're in the land of approximations now. So I'm just going to keep it going with the land of approximations. Oh, actually, that's pretty handy. So if I have 3.0121 minus 3, now I need more. Oh, it was just a 0, so yay. So if I subtract these two, I'll have 0.01210, and then we'll see how badly a decision I made by doing this one without this one, because I can't get this one back because I put in. This is what happens when I have to do problems this early in the morning. So I'll have 0.01210 multiplied by 10, so 0.1210. Now what we want to do is follow this up with the tangent line calculation, which is not really a tangent line calculation, but this would be using 2 points. So this would be like our secant calculation. Now we're going to do the tangent calculation using the thing that we just learned in this section, even though it was a couple of days ago. So part C is where we're going to build the gradient and find the dot product of the gradient and our unit vector. So fx at xy will be 1/2 the square root. It's not the square root. Well, it is going to be a square root, but it's going to be in the denominator. 1/2 the x plus y to the negative 1/2 times the derivative of the inside, which is just 1. And fy at xy will be the same. I realize that finding these derivatives was not the point of this problem, but having all these symmetric things is one of the things that really bugs me about this particular book. Later on, we're going to be doing double integrals, and both x and y will be from 0 to 1, thus disguising whether you understand what's going on or not, or build things correctly. Well, that's a complaint for later. So our gradients will be fx in the I direction. So 1 over, I'm not even sure how I want to write this. I'm just going to write it as is. X plus y to the negative 1/2 I plus 1/2 x plus y to the negative 1/2 j. Our unit vector is the one that we had before, -1 over root 17 and 4 over root 17. I do need to evaluate the gradient at the point 6,3. Spelled 3 wrong. So I get 1 over 2 times the square root of 9. So 1/18 I plus 1/18 j. And I want the dot product of this and our unit vector in the direction of v. So fv at the point 6,3, spelled 3 wrong again. Be the dot product of these vectors, the gradient at 6,3 and the unit vector in the direction of v. So we'll have -1 over 18 times 17 plus 4 over 18 times 17, or 18 square root of 17. It's plus 3. Suppose I should dump a 3. Now this should be close to our approximation, 0.1210. So let's find out. Rats. So this means something went wrong. Oh, and I don't have anybody in the room to tell me where I went wrong. Oh, here we go. Got it. 6 plus 3 is 9, and the square root of 9 is 3, and 3 times 2 is not 18. Three times 2 is what, 6? Is it 6? Those are 6s. These should be 6s. So this should be a 6. So this is a 6. So this is going to be a 2. Ooh, that was close. So this works out to 0.1213 to 4 decimal places. So you may have had different values on your homework problem, number 5 from chapter 14, section 4. But these are all the basic things that you want to do. Mainly the thing, to make this work out, remember you're giving these answers to a computer. So you're going to want to make sure that you carry your decimal places on your calculating machine. Don't start rounding off before it's time to round things off. They're trying to protect you. The problem was actually written to try to protect you because they said round Q off to 5 decimal places. And then the next 2 problems round to 4 decimal places. So whenever you see a problem stepping down like that, you should be thankful that the person that wrote that problem says, I'm going to give you a little cushion at the beginning so that it'll work out better later on. But yet they didn't have enough sense to say, give the exact value and then follow that up with round your answer to 4 decimal places. But you can see why that is, because it's really easy to come up with the exact value, 1/2 root 17, and then miss the entire point of the problem. The whole point of the problem was to have our exact value end up being close to our approximation. And we can see that we're only off by 3 tenths, hundredths, thousandths, 10 thousandths. So that was the point of the problem. So they're like, oh, wait, we should have them round that one off because they'll come up with an exact value for this. Any questions? How's everybody okay? Anybody not okay with me leaving a radical in our denominator? I don't really worry about radicals and denominators anymore because we all have calculating machines. It used to be a big problem leaving a radical in the denominator. In case you're wondering why we rationalize, if I have to approximate 1 over the square root of 2, the denominator is a very bad place to be rounding stuff off. So the square root of 2 is 1.41421 and then a bunch of other stuff. It's irrational. It goes on forever and doesn't repeat. So if I want to make this approximation, I have to do this long division, 1.414 into 1. So not only do I have to know my 1.414 times tables, if I want to improve my approximation, I've got to do my division all over again. And now in my new approximation, I've got to know my 1.41421 times tables. Meanwhile, if I rationalize, now my division just has 2, and I have to know my 2 times tables. And if I need a better approximation, we just start grinding out the numerator. None of this matters really anymore, because if I want to know 1 divided by the square root of 2, I just have the machine do it. So that's the importance of, or the lack of importance of rationalizing denominators in this day and age. 707, 106. Any questions? On the other hand, it's super important to know how to rationalize things, especially when there's more than one term in your rationalization. Because if we have an expression that says like 5 over 2 plus the square root of x, then we know that we can rewrite this with a 2 minus square root of x and a 2 minus square root of x. This was important in limit calculations. 2 is a terrible choice. Doesn't matter. So it's important in this situation when we were evaluating limits and we want to understand the limit process to have this algebraic skill. What's funny is that we teach this process for rationalizing denominators. And say, hey, remember, we could use the difference of squares. Then we also teach you how to factor sums and difference of cubes. And then never ask you to rationalize, let's say, 8 plus the cube roots of x. And it's like, come on, man. If you're going to have people do this, do one, why not do the other as well? If you taught them cube roots, I want something that'll come out 0 in the denominator. So down here, oh, I do want 2. Fuck. So we learn to rationalize, and we see that it's based on the difference of squares. Then at that time, we actually teach people how to factor the sum and difference of cubes, but never follow it up with rationalizing this cube root. It's crazy, the weird stuff that we do. It clearly shows that we had plans before, but we started just like cutting things off the edges of our math classes. Because we ask you to factor the difference of cubes and don't ask you to rationalize when the difference of cubes might be useful. It's really weird. This weird hodgepodge of things that we teach you. Any questions? So in addition to these questions of just doing calculations, calculating the directional derivative of a function at a point in a given direction by taking the dot product between the gradient and a unit vector in the direction you're interested in, you want to remember why it makes sense to make this calculation. You want to remember what the point of the dot product is. The dot product tells you how much of one vector is going in the direction of the other vector. How much of one vector is going in the direction of the other vector. And it comes all the way back down to your horizontal and vertical components. We know that the horizontal component is going to be the magnitude of f times the cosine of theta. Usually when we talk about this as the horizontal component, since it's understood to be horizontal, we don't worry about the fact that this is in the I direction. But really, we can think of this as a specific case, this magnitude of f times the cosine of theta as a specific case of this dot product business. It's a directional derivative. It's just the vector that we're going in the direction of is the vector I, which is a unit vector, and it's horizontal, which is why we don't even bring it up. This is just the FH is just the derivative of, should I say F? It's kind of a vector. The derivative of the function in this horizontal direction. So this is using the dot product. It's just that it's dot I. Because the other dot product is the magnitude of f times the magnitude of I times the cosine of the angle between them. How much of one vector is going in the direction of the other vector? That's what we're calculating with the dot product. How much of this force is going in the horizontal direction? All we do now in 14.4 is take this, instead of having a horizontal direction, have some other direction. What if it's now 4I minus 2j? Or how much of f is going in that direction? So once again, something masquerading as new is just old being updated. I told you Calc 3 was the easiest part of calculus because we're just upgrading our old stuff. Looking ahead, the other reason that I want to emphasize this dot product is just how much of this one vector is going in the direction of the other vector, is that the dot product is a kind of multiplication. And this is a calculus class. One of the other big questions of calculus class is integral stuff. And integration is just multiplication, where one of the factors is continuously variable. So I'm just going to start doing integration where I'm calculating a dot product. And I want to know how much of one vector is going in this other vector's direction. We're going to be extra fancy, and both of those things are going to change continuously. But before we can do that, we're going to have to learn how to describe a bunch of stuff. Any questions? Always stop and take a look for the big picture. Because of the Muppet Show, I can only read the words in space as in space. So this is not gradients in space, this is gradients in space. I don't think anybody here is old enough to have seen the Muppet Show, but there was a segment called Pigs in Space. That's how they announced Pigs in Space. We're now in space. We're talking about gradients. Suppose fxyz is a function. And I want to make the gradient of f. This is what we had before. I think, man, what are we going to do now? If you guessed, I don't know, the same thing, then you are correct, because that's all we ever do. We're going to have to upgrade some more stuff, though. This gradient has an I, a J, and a K. We got dealing with a function of X, Y, and Z. We're not talking about a two-dimensional surface in three-dimensional space. We're not talking about a three-dimensional solid in four-dimensional space. Let's remember what the gradient of a function of two variables told us, or what a function of the gradient was telling us. The gradient tells us the direction of maximum increase. That is still the case. it would kind of be really horrible if adding another direction, adding another variable like this, changed what the gradient meant entirely. That would be horrible. In math, there's some notation that we use over and over again, but that would really mess things up if gradient meant one thing here and something else over here. It's not like this is the English language where you can change the entire meaning of a word just by capitalizing it. The other thing that we had with the gradient was that the gradient was perpendicular to the contour. The contour was where the function wasn't changing. So tangent to the contour, the directional derivative is 0. Perpendicular to the contour, directional derivative is maximum. And that goes along with our cosine of theta business. Cosine of 0 is 1, that's maximum value. Cosine of 90 is 0, that's minimum value, minimum positive value. We can go down to negative. So our direction of maximum increase was perpendicular to a contour. The same thing is going to happen with a gradient of a function of 3 variables, but we're no longer dealing with level curves. Now we have level surfaces. Everything goes up by 1. So our gradient is going to be orthogonal to level surfaces. Just a straight upgrade from our gradients in the plane. Mechanically, we should expect some things to be very similar. Any questions? Now we should expect more talking to come over. Wow, aren't you going to reinforce this? Michael, no. This is where we need to start. We need to see gradient in space. We're dealing with a function of 3 variables. We need to see all the upgrades. F of xy is a 2-dimensional surface in 3-dimensional space. The gradient will be perpendicular to the level curves. F of xyz is a 3-dimensional solid in 4-dimensional space. The gradient is going to be orthogonal to a level surface. Level surface just means a constant value for our function. Just like a gradient was perpendicular to a level curve where f of xy is equal to some constant. Direct upgrade. Any questions? Comments? Snide remarks? All right, tomorrow we should be back to normal, being partially in the classroom, projecting on the screen, and also partially zooming in, projection on the Zoom. Fingers crossed. That's it for today. I'll see y'all on tomorrow. Everybody have a good day, and thanks for playing.